Hello everyone. So this video is basically an extension to the previous video where we started to talk about equivalence relations. So I thought it was a bit confusing as to um, what is equivalence relations equivalence. So equivalence is basically from the term equals to, and to say relation. Uh, to say relation equivalence, we need to. So we went through this example in which you have a set, and then that set um, it's divided into partitions, the union of which is creates the set, and the intersection is an empty list, an empty set. Um, and it's giving us, and we have this example here of A being this set, and we have these partitions of this set. We say that um, so we either use this symbol R or the hyphen, not the hyphen, the curly hyphen, I think. I'm not sure what it's called. But yeah, we use this or that to indicate that there is a relation of equivalence between 0 and 3. So as you can see, it doesn't really, equivalence here doesn't really mean that 0 equals 3, but it just means that there is that there is a relation between 0 and 3, that both are equal to each other, and that sense of the relationship. Again, probably this means that the relationship of real numbers, for example. So 0 is a real number and 3 is a real number. So 0 and 3 are both real numbers. And for that, we say there is a relation equivalence. And there is a good explanation. Try to look further on, because as you dive further around here, so since 1 is a subset of the partition, 1 relation with itself, it is a subset, okay? And to say that the relation equivalence is satisfied, you need to satisfy three properties: reflexivity, symmetry, and transitivity. Let me just look for, I've been looking around for um, some other explanations as to what is equivalence relation. So as you can see, it's saying, uh, it basically says that there is equivalence relation means that there is a relationship between uh, two, what do you call it? Where did it go? Between two objects or two things. Yeah, this is the symbol I've been telling you about. So use the R or use this. So the relation, and he said that there's this example. I'm a sibling of my sister, and this is a transitive relations, which means this, your sister is also your sibling. And then there is this there's this example where it says my sister is a sibling of our brother. So that means I'm a sibling with the brother. But it's not reflexive because, as you can see, reflexive means if A and B, B equals C, that's normal. That's transitivity. If A equals B and B equals C, then A equals C. That's basically what the transitivity means. And then you have the symmetric, in which you say A has a relation with B and B has a relation with A. So in this example, the siblings, in this, the example of the siblings, we've said that my sister is a sibling, is a that is my sibling, and that I am her sibling. So this is called symmetry. But reflexive relationship is that when you say A has a relation with A, that's basically what reflexive means. So in this case, in this example, he's saying that it's not sufficing the reflexive uh, property because you can't say I'm a sibling of myself. So that's the basic idea behind this. So I think we should uh, document this here. It's true to say that the equals the least element. That's definition. So if we can show that all of these properties are suffice, then there is an equivalence relation. Equivalence relation R on a certain set. If A is any particular element of the set, then one can ask what is the set of elements that are related to A. This is called equivalence class of A. So you basically group together the properties or the elements that have similar properties to what we're looking for. Suppose A is a set and R is an equivalence relation on A. For each element A in A, the equivalence class denoted the set of all elements X in A such that X is related to A by R. So what it is saying here is that you have a set A and then you have a relationship. A relationship basically a set of connecting parameters, say be it the sibling in the previous example, or be it say sharing a round shape, or maybe any property that connects 2 points, 2 elements together. So A is a set and R is the equivalence relationship on R. So the elements that share the relationship is called the equivalence class of A, which is denoted by the symbol here. So for each element A in the set A, so this is an element in the set A, the equivalence class of A denoted by the symbol and called the class of A for short is the set of all elements. So the equivalence class of A is the set of all elements in A such that uh, X is related to A by this relationship. So all of the elements in X, all elements, so the equivalence class is the element of X, so the elements that belong to A, such that X is related to A by this relationship. So in this case, instead of it saying the class of A, it's saying the class of S, equivalence class of R. To denote equivalence class of A under R. X subset of A
Alright, let's see. Let A equals 0, 1, 2, 3, 4. So this is a set of these elements. And define a relation R on A such on A as follows: 0, 0, 0, 4, 1, 1, 1, 3, 2, 2, 3, 1, 3, 3, 4, 4, and 4, 0. So the directed graph of R is as shown below. As can be seen by inspection, R is an equivalence relation in A. Find the distinct equivalence classes of R. Hmm. Connected graph for R shown below. So relation R and A. So this is a relation on A. So this is the set of A, and these are the relations. Equivalence relation on A. Find the distinct equivalence classes of R. Okay. Equivalence class of every element. So we've got 0, 1, 2, 3, 4. So 0 we got 0, 4, 1, 3. Why not 3, 1? I don't know, I think I need to read more about this. Hmm. Let's see. An equivalence relation is a binary relation. Two sets A and B is a set of ordered pairs consisting of elements A of A and elements B of B. Short, it's a subset of the Cartesian product. It encodes the information. Okay. An element A is related to an element B. Pairs belong to, let's see, belongs to the set. Okay. There is reflexive, symmetric, and transitive. The relation is equal to but for any object A, B, and C. Okay. Transitive, flexitive, and symmetric. As a consequence of the reflexive, symmetric, transitive, any equivalence relation provides a partition of the underlying set. Okay, that I understand the concept, but I can't seem to get my hand around. Okay, so these are the notations. Maybe this could uh, clear things for us. Various notations are used in literature to denote the two elements A and B of a set are equivalent with respect to an equivalence relation. So the equivalence here is based on a relation or a set of rules that need to be sufficed, right? Okay, the most common A. Uh, these are the common notations. This is a three-line symbol. It's weird, which are used when R is implicit. Okay, variations are specify R explicitly. Non-equivalence may be written. Okay. A given binary relation in a set X is said to be an equivalence relation if and only if it's reflexive, symmetric, and transitive. That is, for all A, B, and C in X, X together with a relation is X together with a relation is called setoid. Now this is where things get a bit confusing. Like X together with, like what the hell is X? Now X is the set, right? And set X together with a relation is called setoid. So with the relation equivalence, the equivalence class of A under the relation is called this. Class equals B belongs to X such that A is related to B. Okay. Equivalence, as you can see, A equals. Simple example. Let's start with a simple example. Let the set A, B, and C have the equivalence relation AA, BB, CC, BC, CB. So these are the relationships. The following sets are equivalent classes of this relationship. But what did you do? Nope, not what we're looking. So we know the concept, we understand what does it mean, and we understand basically everything about it. But the only part we're missing is like, what is it? What does it mean? Like, I think we should explore further. Try to find a good source that really explains this. Uh, Maybe we could opt for a YouTube video. What did it say? It's weird. What the hell? Wait. Oh, I see what it's doing here. Because in the question it says let A and B belong to real numbers. But suppose that A is related to B, a relation to B, if so A and B are related to each other if the subtraction belongs to the integer set, to the set of integers. So in this case you got the 2, so 5.2 and minus 3.2, which are real numbers. The subtraction of these two leads us to 2, which is a positive number, which is a natural number, which is an integer. So the z is a symbol for integers. In that sense, there is a relation between 5.2 and 3.2. However, in this case, the result is 2.1. So 2.1 is not really an integer, so there is no relation between 4.2, 4.1, and 2. Flexive? Mm, yes. Suffices the rule, basically. Mm-hmm. 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 Yeah. Mm-hmm. A minus B equals B minus. So we added both of these. RST. Wait a second, before we get into the solution, we need to, the question is supposed to people are said to be birthday related if they have the same birthday. That is, they are born on the same day of the year. Show that birthday relation is an equivalence relation.
So two people, A and B. Okay, so A has the same birthday as A, so that's reflexivity for you. Then if A has the same birthday as B, then B has the same birthday as A, which is the symmetric relation, which is fine. Now assume that A has the same birthday as B and B has the same birthday as C, then A has the same birthday as C, transitivity for you. So there are three people. A has the same birthday as A, reflexive. If A has the same birthday as B, then B has the same birthday as A, symmetric. If A has the same birthday as B, therefore birthday is an equivalence relation. Now let's see this. Let A, B be elements of the set of, what is this? Okay, I'm not sure what the Q is of again. Complex number? I'm not sure. Anyway, so suppose that A related to B if the absolute of A minus B is less than -1. So let's start with the A. So A minus A, the absolute of A minus A is 0. It's not really 1, less negative, so it's not reflexive, hence it's not an equivalence relation. Alright, that looks pretty interesting. So if we try to go back to the slides, in which there was this example where consider the following partition of A. So we got three partitions induced by this partition. Is a subset of the partition. Now this is not really something I was able to understand easily, so alright, classes.
I'm not sure what they're trying to achieve here, man.
Copy this so that I won't forget it. And great source, video source. Alright, so I'll look for other sources and then we can pick this up later then. Alright, this is it for this video. See you soon then. Well, before I stop this, it looks like there are a few things that we probably need to further do. Like, I'll try to find a list of examples that we could do. Like, see what this we're from says. That is a subset of X, ordered pairs of elements of X, satisfying certain properties. Okay. So it's basically just defining whatever we're saying. What we need to do is like figure out what examples we could do. Maybe this. On the face of most clocks, hours are represented by integers between 1 and 12. However, since a day has 24 hours, after 12 hours the clock goes back to hour 1 and starts all over again from there. Thus each pair of hours, such as 1 and 13, 2 and 14, share one number, respectively. The same applies when we are interested in more than 24 hours. 25th hours is 1, so our 37th, 49th. What are we doing here essentially is that we consider the numbers in each group, such as 1 through 3, equivalent. That says that they represent one number in our congruent model of 12. Being representable by one number, such as we see on clocks, is a binary relation of the set of natural numbers, and it is an example of a relation. So, which we're going to study here. Three properties: a binary R and a set A, where if and only if R is reflexive, symmetric, and transitive. The equality relation on a set of numbers such as 1, 2, 3 is an equivalence relation. The should search for this. Congruent modulo. Integral divisible by a number. Hours on the clock, 12. And then when m equals 2, taking this discrete structure course, together. This means there's another equivalence relation. So this guy's using congruent modulo, which is, I'm not sure what to pronounce this, congruent modulo. And we should study this in the next lesson, I guess. Alright then, see you soon. Well, apparently it looks like we're getting the hang of this. So equivalence relation is basically a relation that connects two elements together, A and B, and that you could in which you could suffice three main properties: reflexivity, symmetricity, or whatever it's called, and of course transitivity. So all these three parameters suffice, then you'll have an equivalence relation in which element is related to A, and the class is basically the result of all the similarities of the elements. Alright, so congruent model OM is an example being used here in which we could read more about to get a better idea of what it means in these examples. But if we give ourselves the option, I'll probably look more into this and decide accordingly. Alright then, so until next time. This was a bit confusing, to be honest, but I think we've gotten the hang of it. It's simply because there's these different terminologies that we need to get acquainted with, and the different representations this could have. Alright, so this is it for today. We'll learn more about this in the upcoming videos then. Cheers.